Okay, now the video is on record now. Let me remind you again about the importance of the energy storage system. You know, energy storage is crucial component in the energy infrastructure that is becoming more essential. Currently, the transportation sector consumes about 30% of total energy. I use word energy here because it's not only electricity in any form. I mean, 30% of total energy consumption. And with electricity now globally, it's just 40% around that, about 40%, and keep increasing. As the supply of renewable energy grows, concerns of the performance and dependability of electrical grid infrastructure are growing. And electrical energy storage is a vital instrument for enhancing the flexibility of integrating renewable energy into the grid, improving grid dependability, boosting the usage of renewable energy, prolonging the infrastructure's service life, and improving power quality. You can think that, well, if you install solar cell or even a wind turbine, those things cannot produce electricity all the time. The electricity produced is not constant, right? It's not constant because it depends on the day, well, or the time, right? Whether you have source of energy or not. For example, solar cell, once you have sunlight, you can produce electricity, but if you don't have sunlight, you cannot produce electricity. That's the point. So while you cannot just put everything into the grid. I mean, you feed everything into the grid because the grid, I mean, power grid has no inventory, has no energy storage in the grid. The purpose of the grid is just for transport energy from electricity from one place to other place, from power plant to consumer, but no, no energy storage, no battery inside the grid. I mean, the battery which is large enough to hold or to store all the electricity. So you have to think about it. If you want to increase the ratio, fraction of electricity produced by renewable energy, because renewable energy has intermittent nature. So actually, there are numerous uses of rechargeable batteries. A typical battery consists of a cathode, of course, the cathode, an anode material submerged in an electrolyte, The electrode material store energy, of course, well, because you charge it, you convert, well, a discharged material back to to fresh material. And the electrolyte transport ion between the cathode and anode, of course, it is the main purpose of the electrolyte. While electrons are carried as electrical current via external circuit. And solid state cathode and anode material are most often used in rechargeable batteries, like in lithium ion batteries, lead acid batteries, sodium sulfur batteries, nickel cadmium battery, and others. Example. Do you know what type of battery used the most in the real world? What do you think? Can you answer my question, Dong Hun Lee?
Yeah, okay. I think
What
it's
type? Yeah.
Lithium-ion batteries.
Wow. Why do you think like that? Why do you think lithium-ion batteries? Because you heard it very often, right?
Yes, and
okay.
use, yeah.
The most, I mean, the most used battery is lead acid battery. Every car has a lead acid battery. And the amount of car, the number is really large. So that means lead acid battery still has a high fraction. Okay. And of course, people talking about lithium ion battery because lithium ion battery used in the, various portable device. But still, lead acid batteries still have a high fraction compared with other type. And the lead acid battery is now the most widely utilized technology due to its low cost and broad range of use. But however, the shallow charge discharge capacity and short cycle life and usage of toxic lead restrict lead acid battery technology. And lithium ion battery and flow battery are lithium ion battery and flow battery are the two significant technologies for future application. Future application we're talking here is for automobile and stationary to back up the power grid. Although flow batteries have received many positive reviews, there are still concerns about technology future when compared to lithium-ion batteries, and questions remain about breakthrough required to allow large-scale deployment. And here is comparison between enclosed battery or traditional battery. You might think about it, and flow battery. In flow battery, the active material stored outside the cell. You see here, this part, an electrolyte tank, for anode and for cathode. And you see that, if you want to scale it up to larger capacity, you don't have to scale the cell. You have to scale up the tank instead. So that means, for battery with larger capacity, very large capacity, the cost is really cheap compared with other type of battery because you store the active material outside. And for this type, for traditional enclosed battery, you see that if you need larger capacity, you have to increase the cell, increase the number of the cell, and the cell itself contribute to a large fraction of the total cost. And battery can be made with a range of solid and liquid electrode materials combinations. In flow battery, the cathode and anode materials are made of electrolyte solution in which the energy is stored. Electrolyte at the anode and cathode size is pumped through porous electrode located at each side in cell stack, where they are separated by ion exchange membrane or porous separator to prevent mixing. Electrochemical redox reaction occur on the electrode surface here, electrode surface. This unique architecture of flow battery allows independent scaling of the power and energy. As I mentioned, the power is defined by the size and design of electrochemical cell, whereas the energy depends on the amount of stored electrolyte. The energy to power ratio can be varied over a wide range. A high energy to power ratio can reduce the cost of whole system by more than half on an energy basis. On the other hand, because they are particularly well suited for small and intermediate scale applications and for short-term duration and fast response time, lithium-ion batteries are well positioned for applications in the electronics and automobile. You can imagine that, for lithium-ion battery, everything is packed inside the cell. So the size of battery will be small. However, scaling up lithium-ion battery is difficult and requires additional management systems for small format battery. Actually, there are other configurations called hybrid flow battery and semi-solid flow battery. For a hybrid flow battery here, well, the cell is made of liquid electrolyte and half of it is made of solid electrode material. But in the case of semi-solid flow battery, the active materials are dispersed in electrolyte. You can see that, well, our active material actually is solid, but it's small size of solid particle suspended in the electrolyte. In this case, we call it semi-solid flow battery. Okay, so while because of good safety characteristic and high power density, aqueous system, when we say aqueous system, we mean, wow, the electrolyte is aqueous-based electrolyte. It's aqueous solution, something like that. So aqueous system have attract widespread interest because of what? Because it's safety, high safety, and it is cheap. It might be cheap for sure because, well, water is abundant. And one of the disadvantage of this system is the lower energy density. This figure here shows the potential of traditional redox couples made of inorganic materials. Most of the materials are still too expensive within the stability window of water. The most widely studied redox species, vanadium is expensive and toxic in its oxidized form. Ideally, low-cost, environmentally friendly species made of iron, zinc, manganese, or sulfur could be used. There have been great interest in completely or partially replacing vanadium with iron. However, hydrogen forms at the anode of the iron-based system still a problem. You can see that if we choose zinc and bromine as our active material, zinc, well, is our negative, bromine is we use it as our positive electrode. The difference between electrode potential of each species define the voltage of the system. Well, if you subtract the electrode potential, of course, you got the OCV. OCV is open circuit voltage. But of course, once you discharge the system, this gap will be smaller because of polarization effect. And while if you start charging the system, the gap is larger, become larger. And the same reason because of polarization, but in different direction. For vanadium, you see that it depends on the species of vanadium you use. For this vanadium 3+ to 2+ and vanadium oxide, the gap is about 1.26 volt. And you see that for inorganic material here, of course, there are a lot of inorganic, more than what listed here, but you have an idea how to design your battery, right? And well, for vanadium flow battery, because when we talk about flow battery, most of people think about vanadium flow battery, which is the first technology categorized in the flow battery system. For vanadium flow battery have been widely investigated because electrolyte on both anode and cathode sides use vanadium species. Here on this catholyte, we use, I should explain about the word catholyte and anolyte first. When we say catholyte, well, we mean the electrolyte at the cathode, and anolyte is, well, the electrolyte at the anode. Okay, so, well, we use the word catholyte and anolyte. Okay, so, well, because we use the same species, right? The same vanadium on both sides. And of course, once the battery operate, you can expect the crossover of species from both sides, right? Vanadium, fresh vanadium here can cross over to the other side also beside the proton. And well, if we use vanadium on both sides, if it mix, we don't have problem at all because, well, you mix vanadium with vanadium, but different species, then it's waste treatment is very simple because you can convert it back to, well, in the same state, just like that. You don't have to separate it because they are all vanadium. Okay. So we can, by this system, we can minimize crossover contamination. Why the traditional vanadium redox flow battery was first scaled up to 250 kilowatt to megawatt hour for demonstration in 2004. Well, almost 20 years ago. There's still a concern about the high cost because vanadium is not cheap. And low solubility and precipitation of vanadium with oxide, V2O5, over a wide temperature range. The low solubility of vanadium ions limits the system to a low energy density of 25 watt-hour per liter. You know, because our active material, it's dissolved in the electrolyte. So solubility is a critical parameter in this case. And the potential for precipitation of V2O5 in the catalyte when electrolyte temperature exceeds 40 degrees Celsius for an extended period of time may reduce reliability and battery life. Recently, a mixed acid vanadium redox flow battery was reported. So, in which chloride ion were added to adjust the sulfation structure of vanadium ion in the solution, thus increasing the solubility. So the key point is solubility in this case. Okay, because our active material is dissolved in the electrolyte. The energy density of mixed acid vanadium redox flow battery was increased by more than 70% relative to traditional VRB vanadium redox batteries, while expanding the temperature operation window by 80%. You know, by adjusting only the electrolyte, by adding acid. The mixed acid system has been successfully scaled up and is commercially produced. Still, as mentioned earlier, vanadium is expensive. The ultimate solution is to find highly soluble, low-cost redox material for aqueous system. In addition, Nafion membrane are used in this system. Nafion membrane used here as our separator, and the main task of Nafion is just to allow proton to cross, right, to transfer across, but prevent other species. And well, the point is Nafion is expensive. And the other thing is Nafion, the conductivity, I mean, ionic conductivity of Nafion is limited and not selective enough. Well, so we expected to increase ionic conductivity of Nafion and of course, lower the cost of Nafion. Okay, so Nafion happened to be the second most expensive component in the system. Capacity fading originating from ion crossover is another problem, and it can be, well, it cannot be avoided because of the poor ion selectivity. So if we improve the membrane here by increasing selectivity, we can reduce the ion crossover and can retard the capacity fading. And of course, that membrane must be chemically stable and highly ion selective. The next thing is, well, here. In traditional flow battery systems, such as vanadium flow battery, energy density calculation include two liquid electrolytes on both sides, right? Anolyte and catholyte. However, for a hybrid flow battery design, energy density is determined only by the liquid volume on one side here, liquid volume here, because the other side is solid. In this design, one half cell features a solid electrode and the electrolyte possess and bipolar and bifunctional characteristics. In such electrolytes, cationic and anionic ions from a single soluble compound are both energy-bearing redox active species, thus eliminating the need for non-active counter ions such as chlorine or sulfate ion that are commonly used in vanadium flow batteries. So this design minimizes the amount of electrolyte in one half cell and achieve a high active species concentration in the other half cell. Example of this system is zinc bromine flow battery, where the system uses zinc as solid electrode and use bromine, which is liquid, at the other electrode. When the system are being charged, zinc metal is plated on the anode side of a carbon-based electrode. Meanwhile, bromine ions are oxidized to bromine at positive electrode. And during the charge, the reverse process occurs. And this system has a high cell voltage and energy density, and expectation are the low-cost material can be used. However, demonstration of zinc bromine system has been limited because of material corrosion. You can think about it because you can expect that because bromine is corrosive. And we also have problem of dendrite formation and electrical shorting, high self-discharge rate, low energy efficiency, and short cycle life. The existence of corrosive bromine at the cathode side is the cause of some of these problems. At the cathode side is the, bromine, right? So expensive cell electrode, membrane, and fluid handling component are needed to withstand the chemical condition of bromine, which is corrosive. And the other thing is bromine has limited solubility in water, and it's of course toxic. Therefore, it is critical that organic agent be used to complex the bromine to mitigate the crossover contamination and toxicity of bromine when it sinks to the bottom of catalyte tank. But of course, this structure, it's shows high potential because we can reduce the size of the system, half of the system. All we have to do is just, select the right material, right component for both anode and cathode. And besides zinc bromine redox couple, here it's zinc bromine, right? Besides zinc bromine redox couple, a novel zinc iodine system in which bromine was replaced with iodine soluble triiodide redox couple has been developed. Here we have zinc and iodine, and this system is also hybrid flow battery because, we have zinc plated on this side, and the other side, iodine is not liquid, is not in liquid state at room temperature, but we can dissolve it, okay, by in a form of triiodide. So for this system, a high energy density of more than 150 watt-hour per liter is achievable based on the high solubility of zinc iodide electrolyte. The ambipolar and bifunctional designs of zinc iodide battery use zinc ions as both redox active species and charge carriers. eliminating the need for non-active counter ions. Together with the high selectivity of Nafion membrane against iodine and iodine ions. Wow, Nafion is very effective here to prevent iodine ion because iodine ion is bulky. It's quite large. And the zinc iodine battery system deliver a high Coulombic efficiency, while close to 99% Coulombic efficiency. And the cell show excellent cycling performance. So this one, okay, while compared with bromine, this one has higher potential. Okay, but you see that iodine bromine is in the same group. It can accept only one electron. It can accept only one electron. That means, well, for one molecule of active species, it can accept only one electron. So, well, in terms of energy specific capacity, it's not so good. But in terms of other things like Coulombic efficiency, the system show very good performance. So, although inorganic redox material like bromine, iodine, vanadium, well, another transition metal, inorganic redox material have attract widespread attention, but organic redox material can offer more flexibility because we have abundance of carbon, right? We turn those carbon to organic material and we can use here. That will be good. As I said, they can offer more flexibility to tune the redox activity, solubility, and stability. Example of organic in this class is quinone. Quinone derivatives are attractive because of their low cost. Well, for quinone, it is just $5 or $10 to $10 per kilogram of quinone. Well, compared with vanadium, vanadium is well more than $30 per kilogram. So you see that quinone is by far cheaper than vanadium. Moreover, quinone derivatives are available from biological process. And you can see that, well, for this system, a system of AQDS, AQDSH2, well, it can convert, right? It's a redox couple. AQDS with bromine reveal a high rate of 2 electron reduction on a carbon electrode surface. The cell was demonstrated for 50 cycles with an OCV of about, well, less than 1 volt, about 0.8 volt, and approximately 99% capacity retention per cycle, which is really high. It also demonstrated 0.6 watt per square centimeter at 1.3 amp per square centimeter, which is quite large current density. Recently, the power output of quinone bromine system was increased to 1 watt per square centimeter at 4 amp per square centimeter, maybe higher than this one. This one is information at two years ago. And crossover of bromine or bromide ion and decomposition of quinone molecule contributed to capacity loss. One obstacle in aqueous quinone-based battery is the low water solubility of quinone. So choosing a substituent to modify quinone-based molecule appear to be one of the most promising approach to overcome the solubility challenge. Substitution of hydrophilic groups such as hydroxyl or amine could increase the solubility of quinone derivatives. And moreover, full substitution are more useful than single substitution in improving solubility of quinone derivative in water. Functionalization away from ketone group provide molecules with the highest solubility. And the results of quinone system also suggest that other water-soluble organic molecules should be studied. particularly those that can be produced from natural products. Well, in this system, you see that in aqueous flow battery, the cell potential is constrained by water electrolysis. Therefore, some recent efforts have shifted to developing non-aqueous redox flow batteries because of the potential to achieve high energy density due to their wider electrochemical window. And you see that this graph shows what is it? Electrode potential versus potential of lithium. If you use all these organic material with lithium, well, we see that the voltage obtained from the system. Okay, this figure shows a redox potential versus lithium plus of representative redox active organic and organometallic compounds. The organic and organometallic compounds have a wide potential window in the range of, well, 0.7 volt to 4 volt, well, more than 4 volt. And the redox potential of promising candidates used as anode and cathode material should be lower than 2 volt and close to or higher than 4 volt to achieve high cell voltage, which is greater than 2 volt. Some of the organic material with proper modification to tailor redox potential solubility and electrochemical activity have potential for non-aqueous redox flow battery. The first study of a flow battery with a metal ligand complex, it's ruthenium bipyridine, was performed. This flow chemistry exhibits an OCV of 2.6 volt and low efficiency, about 40%. Thereafter, other metal ligands such as ruthenium, vanadium, chromium, manganese, iron, and cobalt combined with different ligands, being bipyridine, acetone, phenanthroline. All these non-aqueous flow battery was studied. However, most metal ligand and non-aqueous flow batteries suffer from low coulombic efficiency. That's a point for this class of system due to chemical degradation of the redox molecules and poor solubility. To that, the most soluble transition metal complex examined for non-aqueous redox flow battery application involving multiple electron transfer reach saturation at, well, 0.8 molar in acetonitrile. Synchronous electron transfer complex reach 1.8 molar in carbonate solvent. Acetonitrile and carbonate solvents are the mostly used non-aqueous electrolyte. Their energy density are much lower than those of aqueous system, although cell potential is larger. The complicated synthetic procedure and the inherent low solubility and poor chemical stability of metal ligand complex have gradually shifted the attention of the research community to all organic redox molecules. So one possible direction for future research for both aqueous and non-aqueous redox system could come from the experience in solid organic electrode material for lithium-ion batteries. For inorganic materials, the redox reaction is based on the valence change of transition metal or elemental substance, while for organic materials, the redox reaction is related to the charge state and change of the electroactive organic group. Generally, organic materials potentially used for battery could be divided into several groups: conjugated hydrocarbon, conjugated amine, conjugated thioether, organodisulfide, thioether, nitroxyl radical, and conjugated carbonyl. Among the 7 types of structure, well, organodisulfide and conjugated carbonyl belong to N-type organic materials. It is electron transport. Conjugated amine and conjugated thioether belong to P-type organic. Well, you know that for P-type is whole transport, right? While conjugated hydrocarbons and nitroxyl radicals belong to bipolar organic materials. A reversible redox reaction usually takes place in organic group with conjugated structure and atoms with lone pair electrons, such as O, N, and sulfur, oxygen, nitrogen, sulfur. Because a conjugated structure is beneficial to electron transportation and charge delocalization, and lone pair electrons usually have a higher reaction activity. And the redox molecules could be rationally designed. Some basic requirements for these organic candidates include the following factors. The first factor is electrochemical reaction reversibility. This factor can determine cell polarization. Nitroxyl radical present the highest reaction kinetics. On the contrary, organodisulfide and thioether show slow reaction kinetics because the bond breaking forming of the SS and SO, right, which is double bond, requires a high activation energy. And the next factor is redox potential. And this factor determines the site on which the organic can be used. Generally, P-type organics such as nitroxyl radical have a higher redox potential than N-type organics, for example, conjugated carbonyl. In addition, quinone-based organics, electron withdrawing and electron donating groups can effectively tune the redox potential. Solubilities, small organic molecules tend to dissolve in either aqueous or non-aqueous electrolytes. In addition, a proper substitute or a change of structure symmetrical can effectively increase the solubility of organic materials. And the next factor is chemical stability. This factor is very important for organic material used in long-term applications. Degradation of some radical compound is closely associated with nature of solvent and salts. Okay. So, while in addition, a lack of suitable membrane is one of the major technical hurdles impeding development of non-aqueous flow battery. For porous separators, crossover of redox materials could cause irreversible performance degradation. Two size exclusion-based strategies have been attempted to overcome this limitation. The first strategy involves reducing the membrane pore size to increase selectivity. And the second strategy is to put redox moieties onto polymeric backbones. And this method also try with water-soluble polymers in an aqueous flow battery. However, the conductivity of membrane and the solubility of redox polymers still remain a concern. Well, because of redox chemistry is currently limited by the solubility of the electroactive species. So the concept of a semi-solid flow battery has been proposed. In this system, the particulate active materials are dispersed in the electrolyte as suspension, essentially achieving infinite solubility compared to traditional redox solution. To achieve electronic charge transfer between the active material particles and the current collector, the active material and conductive additive were dispersed in a typical lithium-ion battery electrolyte solution to form a percolation nanoscale conductor network in the flowable electrode suspension. At the high solubility of the active material in suspensions at the high cell potential lead to significant increases in energy density. The semi-solid flow battery still needs to be carefully engineered and optimized. Scale up of the system could still be difficult. Current flow batteries depend on multiple reaction stacks to increase the energy and power capacity. In a semi-solid system, the electrolyte needs to be conductive enough to transfer the electrons. You see that is different from other batteries. Conductive electrolyte system cannot be used in multiple stacks because of the shunt current through the electrolyte connecting multiple series connected cell in a stack driven by the voltage difference between the cell. In addition, the chemistry and the physical properties of the suspension need to be carefully controlled. A high solid loading is normally designed to achieve high energy, but the high suspension viscosity could contribute to pumping related energy loss. So we should think about it too. Right, this pump. Pumping a liquid suspended with small particle will consume a lot of energy. In the next class, I'm going to talk about metal air battery. For metal air batteries are a family of electrochemical cells powered by metal oxidation and oxygen reduction, exhibiting a great advantage regarding theoretical energy density, which is about, well, more than 10 times higher than commercial lithium-ion batteries. For example, lithium air batteries and zinc air batteries are two types of metal air batteries that have attracted most attention currently. For lithium air battery can deliver a superior theoretical performance of large energy density, very large. This number you can think of gasoline. We see that this number approach to gasoline already, and a high specific capacity, with cell voltage about 2.96 volt for lithium air battery. And for zinc air battery, still about, well, the theoretical energy density is 1,350 kilowatt hour per kilogram. This kilogram is a kilogram of zinc because we don't count for air. Still, this number is 4 times higher than currently lithium-ion battery. Moreover, zinc air battery have the advantage of low cost. Zinc costs about 10 USD or less than 10 USD per kilowatt hour, maybe 4 or 5 or less than that, compared with lithium-ion battery, which is by far more expensive. Besides, lithium air battery and zinc air batteries, other types of metal air battery also have their own superiority. For example, aluminum air batteries exhibit the highest volumetric capacity, close to 8,000 amp-hour per liter. And sodium air batteries show smaller charge over potential than lithium air batteries. Well, therefore, metal air battery family has great potential to serve as next generation electrochemical energy storage device. Metal air battery usually contain 4 major parts: an air cathode, air electrode here, a metal electrode on the other side, electrolyte, and separator for parts. For most metal air battery, the air electrode reactant is obtained from the ambient air directly. It's oxygen from air, rather than an encapsulated oxygen in the cell. Therefore, the air electrodes usually consist of only an electrocatalyst layer to reduce the electrode over potential and a gas diffusion layer to enhance oxygen diffusion between the ambient air and the catalyst surface. For highly active material that are unstable in aqueous system, for example, lithium, sodium, and potassium, we use non-aqueous aprotic electrolyte. And for relatively inactive metals such as zinc, aluminum, magnesium, and iron, usually we use alkaline aqueous electrolyte as well in the system. For separator, the separator is an optional component. Optional means, well, sometimes we need it, sometimes we don't need it. Okay. Well, the function of separator is just to separate 2 different electrolytes. Okay, in that case, we need it. And also obstruct some mass transportation process between the electrode and prevent short circuit caused by metal dendrites. And if we have another mechanism to prevent dendrite and prevent mixing of electrolyte, in case we use 2 electrolytes, we don't need separator anymore. So here, the reaction mechanism involved in the system. M in this case, we use M stand for zinc, aluminum, magnesium, iron, and so on. M stand for metal. And N represent the ion charge number. The metal ion generated on the metal electrode during the discharge process may further react with hydroxide ion in the alkaline electrolyte. And on the air electrode, the conversion between oxygen and water take place during the discharge and charge processes, so-called ORR, or oxygen reduction reaction, well, which involve for discharge process, and oxygen evolution reaction, or we call it OER, involved in the charge process of the battery. And among various metal air battery technology, zinc air battery are promising due to their high energy density, low cost, great safety, and environmental friendliness. The cathode active reactant of zinc air battery is oxygen from atmospheric air, which is inexhaustible and can be stored outside until the battery is discharged. And zinc air cells are composed of 3 parts: zinc metal here as an anode, air electrode as the cathode, right? Which is divided into a gas diffusion layer. We have gas diffusion layer at outer part and catalytic layer, and a separator here between anode and cathode. Because of the solubility of oxygen is very low in electrolyte at atmospheric pressure, it is necessary to use oxygen in the gas phase, not liquid phase. Oxygen from atmosphere diffuse into the porous carbon electrode here by difference in pressure of oxygen between the outside and inside of the cell. And then the catalyst here facilitate the reduction of oxygen to hydroxide ion in the alkaline electrolyte, with electrons generated from oxidation of zinc metal as the anode reaction. So this is why we call this process a three-phase reaction, because we have catalyst, which is solid phase, electrolyte, which is liquid phase, and oxygen from gas phase. We have three phase, so we call it three-phase reaction. And this structure favors the gain of oxygen in zinc air batteries. Generated hydroxide ion migrate from the air cathode to the zinc anode. Okay, hydroxide ion generated across the cell, transport across the cell to the other side to complete the reaction. So this overall procedure during discharge can be described as the following: electrochemical reaction. Here. Of anode and cathode in alkaline solution. The equilibrium potential of this system is 1.65 volt, which is the different electrode potential of the anode and cathode, However, the practical working voltage of zinc air battery is less than 1.65 volt due to the internal loss of the cell due to activation and ohmic and concentration loss. It may be helpful to understand the electrochemical behavior of zinc air battery through a schematic polarization curve of each anode here. So this figure shows potential and current. Potential as a horizontal axis and current. Well, we use this figure to understand the major origin of potential loss in zinc air cells. The over potential at the zinc anode here is, you see that it's relatively smaller than for air electrode. Also, the cathode current occurs at the cathode, the air electrode. You see that for discharge process, at the cathode, we have a reduction, right? Reduction process. We call it oxygen reduction reaction. So at the same current, at the anode, we have oxidation. So the discharge voltage is the difference between the potential at the same current between the oxidation of zinc and reduction of oxygen. So at higher current density, let's say this point, this current density, and this one about the same distance here, we can determine if we have this kind of graph, we can determine the voltage, discharge voltage of the cell. Also, during charging, for air electrode, we experience the oxygen evolution reaction, OER. So we have OER on this side. And reduction of zinc occur at the negative electrode. So you see that the voltage difference increasing, right? At higher current density, of course, the voltage increase suddenly. At the anode also, at the zinc electrode also the same way. So you can determine the voltage required for charging process. So there are many excellent studies focusing on challenge facing the development of air electrode, such as the search for carbon alternative or development of novel strategy to achieve highly efficient bifunctional catalysts, because both OER and ORR needs catalysts. Well, so development of novel strategy to achieve highly efficient bifunctional catalysts that can effectively decrease discharge and charge over potential. In contrast, while rather limited works have focused on the challenge facing at the zinc anode, actually zinc electrode are a more serious constraint on the performance of zinc air battery in terms of cyclability. So the failure of battery is generally attributed to degradation of the zinc anode rather than air electrode, because the air electrodes usually have a much longer cycling life than the zinc anode. So while zinc air battery usually use zinc metal as an anode active material, so we expect oxidation of zinc occur during discharge. Although the zinc corrosion rate is slower than that of aluminum in an alkali solution, but this corrosion process generates hydrogen gas through hydrogen evolution reaction. We call it HER. Well, it is more reasonable to consider electrochemical behavior of zinc metal in the alkali electrolyte, not just the zinc metal in the gas phase. So the zinc electrodes suffer from critical problems such as passivation, dendrite growth, hydrogen evolution reaction, or HER, during operation of battery, limiting the practical application by weakening the discharge performance and reducing the shelf life and cycling life of the rechargeable zinc air battery. In practice, the actual energy density of zinc air battery is about 200 something to 300 watt-hour per kilogram of zinc, lagging far behind the theoretical value. Well, the theoretical is 1,000, right? More than 1,000 watt-hour per kilogram. But which remains a challenge to reach and requires substantial effort for their development. The low utilization rate of zinc, which is due to the passivation of zinc electrodes in alkali electrolytes, is one of the important reasons for the difference between theoretical energy density and the actual energy density. So, passivation of zinc refers to zinc oxide being supersaturated in alkali electrolytes and deposit on the surface of zinc electrode to form an insulating layer during the discharge process, which blocks the surface of the electrode and affects its further reaction. We have zinc and we cover it with zinc oxide, similar to this one. And the insulating zinc oxide passivation film terminates the discharge process, reducing the utilization of the zinc electrode and the battery capacity. It also prevents the reverse conversion of metallic zinc, limiting the battery rechargeability. A small number of studies focus on the mechanism of passivation. At high current density, compact zinc oxide layer form to passivate the electrodes. At low current density, porous zinc oxide layers form, and passivation will not occur when the mass transfer of hydroxide ion across porous zinc oxide layer is enough for anodization. The passivation layer is divided into two parts. The inner layer is dense zinc oxide layer, while the outer layer mainly consists of zinc oxide and zinc hydroxide sediments. The mechanism of passivation still needs a deep and unified understanding. The performance of zinc air battery is not only dependent on the zinc electrode, but also strongly depends on the interaction between the electrode and electrolytes of zinc air battery. The composition and concentration of electrolyte can affect the formation process of zinc oxide and further influence the discharge capacity. as well as battery rechargeability. Therefore, to mitigate the impact of passivation on the charge and discharge performance of battery, zinc passivation of zinc air battery can be eliminated or decreased by the design of metal anode materials and modification of electrolyte composition. Well, zinc electrodes are in close contact with the electrolyte. So the zinc electrode passivation can be inhibited by modifying or adjusting the electrolyte composition. So in general, if we use, well, there are many approaches to suppress the zinc oxide passivation layer. Well, such as improving the electrolyte concentration, adding surfactant to the electrolyte, and producing liquid flow to dissolve or destroy the dense structure of passivation layer. Well, among these methods, using a high concentration of alkaline electrolyte, in this case we use KOH, to increase the solubility of accumulated zinc oxide is the simplest method, because the passivation layer is loose and unstable under high pH conditions. But this method also causes serious anodic corrosion because we use high concentration of KOH, right? So it kinds of trade-off between corrosion and passivation. The other method is we can use additive. We add additive to electrolyte by adding the appropriate amount of surfactants to the electrolyte can cause the passivation layer to become loose by preventing zinc oxide precipitation on the active zinc surface, which reduce the influence of the passivation layer on diffusion ability of the zinc ions generated by the discharge reaction diffusing into the electrolyte, and reduce the diffusion resistance of the passivation layer on discharge products. The frequently used surfactant in zinc air battery can be divided into 3 categories. The first one is cationic surfactant, such as DTAP. DTAP is dodecyl trimethyl ammonium bromide. And CTAP. CTAP is cetyl trimethyl ammonium bromide. And the next category is anionic surfactants, such as SDS, sodium dodecyl sulfate, and dodecyl benzene sulfonate, SDBS. And the last category is non-ionic surfactants, such as polyoxyethylene, nonylphenol, and puronic. Well, the above surfactants can significantly suppress the passivation and corrosion of the zinc anode in a dilute alkaline electrolyte. Because they absorb surfactant molecule can prevent contact between water and the anode. Some studies have suggested that anionic surfactants outperform cationic surfactants in enhancing the cycle life of the batteries, because the negatively charged polar group of SDBS coordinate to zinc ions at the anode surface, leading to the generation of small zinc oxide particles that effectively inhibit the growth of the passivation layer. In contrast, the positively charged polar group of CTAP shows weak interaction of zinc ions, leading to generation of larger zinc oxide particles. In addition, surfactants with multiple anchoring groups have advantages in binding the anode surface to inhibit the formation of zinc oxide passivation layer. In addition, for flow battery, for zinc air flow battery, the convection condition of the electrolyte also have an impact on the physical chemical property of the zinc passivation film. A flowing electrolyte reduce the effects of a passivation layer by removing loosely deposited passivation layer and reducing local concentration gradients. And the next thing is next approach is to use modified anode for passivation inhibition. The development of modified metal anodes is an effective means to improve the capacity and rechargeability of batteries. The preparation of modified anode includes the tuning of the zinc anode structure and surface modification of the anode particles. Tuning the zinc anode structure refers to development of porous active anode material with high surface area. And surface modification of the nano-sized anode particles refer to cladding zinc anode particles with various ion-sieving nanoshells. The selection of ion-sieving nanoshell components such as the graphene oxide, titanium nitride, titanium oxide coatings, carbon coatings, silica-based coating, and ionomeric hydroxide conducting polymers is required to create desirable environment for the free transportation of electrons and therefore make zinc oxide electrochemically active. And the next problem related to zinc anode is dendrite formation. Dendrite formation on the anode surface generally occurs in alkaline zinc air batteries during charging. The formation mechanism of zinc dendrite has been studied. The charging reaction of the zinc electrode is mainly influenced by the liquid phase mass transfer, in which large concentration polarization forms in the low concentration of active component near the electrode surface. And the active components in the electrolyte are more likely to diffuse protrusions on the electrode surface, where the current density is much higher for reaction, resulting in uneven current distribution on the electrode. The deposition of zinc is sped up on the tip of the electrode to form eventual dendrites. During the charging process, the deposition morphology of the zinc electrode varies with the current density. That means while you change current density, you can modify the structure of deposited zinc. And the dendritic morphology does not form at low current density due to low activation over potential. A leaf-like morphology is easily formed at high current density, demonstrating the dendrites symmetrically grow on both sides of the main stems. Such fractal growth may stem from powerful surface energy anisotropy, leading to limited diffusion of atoms. Generally, dendrites are axial and needle-like single crystal with flat step top. The growing dendrites will cause the battery short circuit and deteriorate electrochemical performance, which result in a short battery life. In addition, dendrites are easily detached from the electrode, resulting in attenuation of the battery capacity. And the harm of dendrite growth to the battery can be mitigated by physically blocking the contact between the electrolyte and electrode by changing the electrochemical deposition behavior of zinc in the electrolyte. Currently, while researchers mainly use polymer separator and introduce different additives in battery system to reduce the harm of the dendrite problem. A polymer separator can be used to inhibit the penetration caused by the growth of dendrites by building a physical barrier. The polymer separator used in zinc air battery mainly includes the PVA membrane, a PE membrane, or hydrate cellulose membrane. In addition to applying commercial separators such as Celgard, Nafion, or polyvinyl alcohol, various preparation methods of novel separator with high anion selectivity and low ion resistance have also been developed. However, the polymer separator cannot fundamentally prevent the formation of growth of zinc dendrites. Therefore, it is better to utilize it together with other methods. The introduction of organic and inorganic additives to the electrode and electrolyte can inhibit zinc dendrites by changing the electrochemical deposition behavior of zinc in the electrolyte. Recently, some organic agents have been added to the electrolyte to deposit a flat zinc-based film composed of small grains by influencing the electrochemical properties of zinc electrodes during electrode deposition, such as the grain size, chemical composition, and anti-corrosion property. And the other things, so ionic liquid. In ionic liquid, well, if we use ionic liquid, we don't experience dendrite formation anymore. But the problem of ionic liquid is, one thing is cost. And the other things of related to ionic liquid, it's well, low ionic conductivity. So while for ionic liquid, we have to compensate. We have to increase the ionic conductivity of the system. As I mentioned before that, well, for at the cathode, it involves oxygen reduction or evolution, whatever. Depends on charging or discharging. And rechargeable zinc air battery used bifunctional oxygen electrocatalyst as the air electrode in for charging and also discharging process in order to facilitate the sluggish reactions rates and also improve round trip efficiency because it's reduced over potential, right? The fundamental oxygen electrochemical reaction that regulate the operation of rechargeable zinc air battery are oxygen evolution reaction and oxygen reduction reaction, corresponding to discharge and charge process. The function of oxygen electrocatalysts are critical, important, really important for practical operation of rechargeable zinc air battery because of the intrinsically sluggish kinetics of the uncatalyzed OER and ORR. OR in an air electrode proceed in several steps, you can see, the same way as OER. It's complex, it's quite complex and depends on the catalyst also. In alkaline, in SAP, zinc air batteries, OR occurs in a series of consecutive steps. First, diffusion of oxygen to the three-phase battery from the atmosphere, and absorption of the oxygen to the three-phase battery, and electron transfer to the absorbed oxygen. And the last step is elimination of hydroxide ion from the catalyst surface into the electrolyte. And OR may proceed through the 4-electron pathway, which is the more efficient pathway, or 2-electron route. Yeah, 4 electron or 2 electrons. So for 2 electrons, this process can be denoted as a serial 2 plus 2 electron, 2 electron and 2 electron pathway. And the OR route depends on the configuration of oxygen adsorption that exists on the active site of the catalyst. The two types of oxygen absorption are enough in oxygen adsorption and bidentate oxygen absorption, which lead to the 2 electron route and direct 4 electron pathway. And for the reaction mechanism and pathway of OER are also extremely complex and vary with different electrocatalysts. Oxygen molecules are easier to be evolved from metal oxide rather than pure metals. The multivalence characteristic of metal cation is fundamental because the electrochemical reaction is induced from the interaction between metal cations and oxygen intermediates, which leads to the formation of a bond by changing the valence state. Site geometry of metal cation has significant impact on the reaction mechanism because it affects the relevant coordination number, the activation energy for the oxidation state, and the absorption energy of the oxygen species. So the OER route in alkali electrolyte is discussed as follows. M here represent the active site of the surface of the catalyst, and S here represent the substance absorbed on the surface of the catalyst. Our reaction begins with coordination of hydroxide to the activation sites in the alkali system. Then the next reaction process mainly via 2 ways, 1, 2, 3, or 1, 2, and 4, 5, depends on the route of the reaction or the reaction pathway. Generally, precious metal oxides such as ruthenium oxide or iridium oxide are known to be highly active toward OER because of high electrical conductivity and low redox potential. However, these precious metal-based oxides are very costly and have only demonstrated limited OR activity, insufficient for use as bifunctional catalysts for rechargeable metal air battery. Conversely, much more cost-effective and strongly bifunctional transition metal oxide catalysts such as cobalt oxide, nickel cobalt oxide have shown high activity for both OER and OR with electrochemical stability. The key engineering tasks in technical realization of electrically rechargeable zinc air battery is development of durable and efficient bifunctional air electrode. The air electrode of rechargeable zinc air battery does not have to possess active material because of oxygen in the surrounding air is the active material for rechargeable battery, right? And it's supplied into the gas diffusion electrode. We have gas diffusion layer here, which is one of the great advantages of rechargeable zinc air battery. A bifunctional air electrode consumes oxygen during battery discharge and reversely evolve oxygen and release oxygen while charging. Therefore, diffusion of oxygen is highly important for OR and OER, which are the important reaction in rechargeable zinc air battery technology. However, oxygen in the gas phase and it is typically difficult to be diffused into gas diffusion layer and even encounter in the liquid electrolyte for the completion of oxygen reactions. So the diffusion of oxygen from the air is one of the necessary requirements. In addition to diffusion effect, the air electrode also needs a catalyst which can elevate the activation energy of oxygen reaction. In other words, catalyst can decrease over potential for OR and OER. And the air electrode, which is normally called GDE, is a 3-layer electrode system. It has hydrophilic layer, hydrophilic microporous channel consisting of catalyst particle here, and the hydrophobic microporous channel, which is responsible for oxygen absorption and distribution to the catalyst site, porous hydrophobic layer, and the current collector that evenly spans throughout the electrode to make sure over potential is not localized at certain spots of the air electrode. And for hydrophilic layer, it is vital that the hydrophobic PTFE, polytetrafluoroethylene binder, is kept to minimum to maximize electrolyte exposure at the catalyst site. And PTFE is the only suitable binder now in the case of Zinc Air Battery because of its high corrosion resistance in alkaline electrolytes as well as hydrophobic properties. The hydrophobic layer is engineered in such a way to promote maximum gas intake without leading to electrolyte flooding. Electrolyte flooding will prevent oxygen reaching catalyst sites at the hydrophobic microchannel. Current collectors are chosen based on conductivity and stability of a material. And for current collector, well, we usually use nickel foam because it has high conductivity and also, well, high corrosion resistance, making them ideal for use at the air electrode. The performance of oxygen electrocatalyst at the air electrode is determined by GDL, or gas diffusion layer. Gas diffusion layer should fulfill the following condition: high electrical conductivity, favorable surface wettability, and excellent gas diffusion property, which depends on their thickness also, hydrophobicity, and porosity. For rechargeable zinc air battery, the GDL has the following essential function. First, provides a uniformly distributed transportation of oxygen to and from electrocatalyst, used as physical support for the catalyst layer, and should be highly electrical conductive to supply an electrical conductive pathway for the current collector. And the next thing is prevents the electrolyte from leaking out, serving as a wet proofing electrode. So GDL should be highly porous, hydrophobic in nature, and thin to allow oxygen transportation to from electrocatalyst. Recently, design of gas diffusion air electrode consists of several PTFE bond carbon layers with two interpenetrating microchannel of hydrophobic and hydrophilic layers on current collector layers, well, which is nickel stainless steel mesh, titanium mesh, nickel copper foam, and carbon. Hydrophilic microchannel are properly wetted for providing access to the liquid electrolyte. The hydrophobic microchannel counterparts are designed to facilitate fast air diffusion from the atmosphere to the catalytic site and to provide a barrier to prevent electrolyte penetration. The battery polarization behavior in terms of electrical conductivity, ohmic resistance, and gas permeability mass transfer are influenced by the degree of hydrophobicity and the GDL. And different engineering strategy can be adopted for the engineering of electrically rechargeable zinc air battery. Engineering of separate electrode for OR and OER to solve the problem of stability. And also, while stability depends on chemical or physical. Moreover, OR and OER require different conditions, right? And the next thing is engineering of a multi-layer electrode with separated layer of ORR and OER course. This is similar to the first one, but it's still connected, but different layer. And the next one is engineering of single layer electrode with and bifunctional catalyst for both OR and OER. Yeah. Well, this strategy to solve the problem of bifunctional electrocatalyst. So while Zinc Air Battery bifunctional electrocatalysts need to have a property such as high porosity, optimal bond strength between zinc cations and the oxygen hydroxide species, and a small energy barrier between the inflow chemical and the charge transfer step, and high surface area, of course. The ideal oxygen electrocatalyst should accommodate the following basic criteria. The first one is activity. Well, the catalytic activity is determined by the number of active site, intrinsic catalytic active site. Primarily, the heteroatom doping of sulfur, nitrogen, oxygen, phosphorus, boron, and metal atoms, and defects control like age and vacancy will generate charge redistribution and charge electronic structure, which reducing the absorption energy of oxygen containing species on them and improving the intrinsic catalytic activity. Then control of porous structure, mesoporous, microporous, or macroporous, can also enhance the exposure number density of the active sites. And the macroporous can give more mass transfer pathway, whereas the microporous can give larger specific surface area to increase the accessibility of reactants to active center. And the next thing is conductivity. Of course, superior conductivity is the basic to electron transport in rechargeable zinc air battery electrochemical reaction. And well, what else? We need stability. Of course, zinc air batteries ideal electrocatalysts must have excellent chemical and structural stability in the harsh acid and alkaline environment because of the increase in particle size, the accumulation of particles and the charge, and the change of the oxidation state on the surface of electrocatalyst during the long-term charge discharge cycle of the battery. So the electrocatalyst will gradually age and become inactive, which lead to the loss of battery's performance. And the next thing is selectivity. SAP's ideal oxygen electrocatalyst should have highly selectivity towards specific reaction. And well, we need low cost and environmental friendly precious metal such as platinum, gold, silver. Electrocatalyst possess high catalytic activity, but the disadvantage of the high price, low stability, and limited access seriously restrict their practical application. Okay, so generally we have summarized the recent development by functional OR/OER electrocatalyst as the air electrode for rechargeable zinc air battery from 4 aspects. Well, precious metal-based catalyst, transient metal oxide, zinc mixed metal oxide, perovskites. Well, for perovskite, we need oxide perovskites and spinel. And the last category is carbon-based material, which is, well, become more and more popular recently. Okay, that's all for today's talk. Thank you for your attention. And if, well, these are my sponsor, my university, Chulalongkorn University, and also NXPO, which is funding source for my research, So if you have any question, just, well, raise your question, and I'm more than happy to entertain your question. Any question? Any question from students? Any question from the floor? Well, can I ask you a question? Any one of you while is working on Zinc Air Battery or even other type of battery? No one? Hmm? I think some of you is working on Zinc Air Battery because I know that in your lab also some of you working with catalysts and other in various types of batteries. No? Okay, well, if you don't have any response and don't have any question, we are going to close our talk today. Yeah, I would like to close the lecture and class dismissed. Okay, thank you. I got response from you. Say thank you. I can say welcome. You're welcome. All right. Have a good day. Yeah, and stay safe from virus. Okay. Okay, thank you. Bye-bye.